That seems to have worked. Okay, yeah, there we go. Sorry about that. Getting some weird notification about the microphone not working, but it looks like it's working now. So today we're coming over the crest of the hill. Today we're going to learn the fundamental theorem of calculus, which is a big thing. Also, I know you guys are anxious about the tests. Most of them are graded. All the electronic ones are graded. Most of the paper ones are graded. I think there's still one or two that I'm working through. I was banging the rest of them out this morning. So bear with me just a little bit longer. We are very, very close to having all that stuff done. But the material for today is exciting material. So let's get to it. This is MAC2311, section OH1, Path 1 honors. And the date today is November 17th, 2021. We may or may not finish all of 5.3 here today. And I've spoken a little bit with Daniel about his student teaching and how we're going to proceed. Either Friday, our next meeting will be that student teaching day where we'll learn about indefinite integrals and the net change theorem, or next Monday, depending on whether we get all the way through 5.3 today. But that's what we're doing today, the fundamental theorem of calculus. It's actually two theorems. And that's section 5.3. This is kind of the big payoff for all of the work we've been doing with Riemann sums and interpreting areas and all of that stuff. We're going to connect the objects of 5.2, which were, remember, definite integrals, those limits of Riemann sums. We're going to connect those objects to the things that we learned about last time, the antiderivatives that Talia taught us about. I'm going to bring up your textbook here because I want to follow them quite closely. And we will discuss proofs and everything like that. So the big game here is to take some function little f and integrate it, but not from a to b, not from one constant to another constant, but to integrate from some constant up to a variable. So the main object of study today is the integral from a up to x. And because we're using the variable x as one of the bounds, we don't want to use that as the variable in our integral. That would be kind of overloading that variable, using that same symbol for two different meanings. So that's why you see the variable t inside here. And this, of course, if you have some curve, right? If you look at the graph of f, so this would be my t-axis. This would be y equals f of t. If a is over here, then I can think of x as being a variable able to move around from left to right over here. And then the interpretation is the same as it has been. That definite integral is this area. And you think of this as being like on a little slider. You can move it left or right, and that total area will change. So this area, this integral, it's not a function of t, it's a function of x. If I move x to the right, then that area gets bigger. If I move x to the left, then that area gets smaller. So it's a little bit subtle. Your book calls this thing g of x. And the first thing I wanted to do is just make sure you understand that this really is a function of x. The symbols inside the t and dt, the variable t is what's called a dummy variable, or like an index variable. kind of like the index in the summation. Sum from I equals 1 to 5 of I is the same as sum from n equals 1 to 5 of n. It doesn't matter what symbol you use for that index. What we're going to see, I'll just go ahead and spill the beans, is that this object is an antiderivative for little f. That's going to be the thing we discover. But we're going to get there through a couple examples. We looked at one example already, the integral of 2t, right, where f here was 2t. We saw that integral from 0 to x came out to x squared. And you know that the derivative of x squared is 2x. So I think probably best to go ahead and state the theorem. Maybe one or two other little things. So if f of t is positive, then what can we say about the function g?
Recording in progress.
If this curve is always above the x-axis, or sorry, always above the t-axis, so this area is always positive, as x gets bigger and bigger and bigger, what happens to the area?
Getting bigger.
Yeah, it gets bigger. So g of x would be increasing. Isn't that interesting? Where else have we seen this relationship between positivity and increasing? Well, derivatives, right? So this seems to suggest that f is somehow the derivative of g, which would mean that g is an antiderivative for f. Let's see if there's any other notes I want to make in here. Not really. Yeah, we'll look at that in a minute. No, it's time to just introduce the theorem. Okay. So the theorem says, this is the fundamental theorem of calculus, part 1. So the thing that this suggests is true. If little f is continuous, you could say on the interval a to b, and g of x is defined to be the integral from a to x of little f of t dt, where x is somewhere in the interval ab, then g is differentiable at least, maybe elsewhere, but at least on the open interval from a to b, and g primed of x is the same as f of x. That is, g is an antiderivative for f. So this says where x is an element of or is in the closed interval AB. You could replace this statement right here if you don't. That I know this isn't a notation we've used a lot throughout the semester. You could say A is less than or equal to X is less than or equal to B if you like. So yeah, if f is continuous on AB and g of x is the integral from a to x of f of t dt, where x is in the set AB, or equivalently a is less than or equal to x is less than or equal to b, then g is differentiable, at least on the open interval ab, and g prime of x is f of x. In other words, g is an antiderivative for f. There are only kind of so many interesting questions I can ask you about this theorem. The classic one is just defining a function as an integral and then asking you to calculate its derivative. So sort of a classic example here. I could say find g prime of x, where g of x is the integral from 0 to x of cos t dt. And what we recognize is that the function little f here, f of t, is cos t. So by the fundamental theorem, part 1, I'm going to abbreviate fundamental theorem of calculus as FTC because it's a lot to write. By FTC, part 1, g prime of x should be f of x, which would be cosine of x. So in other words, to differentiate something like this, you just take this variable and plug it in here. The integral goes away, the dt goes away, you take this variable and plug it in here. Sort of another way of writing FTC1 is that ddx of the integral from a to x of f of t dt is f of x. And the blue expression here is kind of the way I like to think about it, because this says that the derivative and the integral undo each other. The derivative and the integral are sort of inverse operations. If you do one and then do the other, you just get the function that you started with. There is this business of the variable changing, and that's the part where I think people get a bit confused. But if you think about it in terms of this picture up here, hopefully it'll make a little bit more sense. So this first example down here, this is sort of the classic problem related to fundamental theorem of calculus part 1. It can be extended slightly using the chain rule. And I'll look at that for you in a minute, but first I want to convince you that this is a true statement. So let me pull the textbook back up and we can kind of look at the proof. My aim is to find the derivative of this function, right? I want to show that g primed is little f. So we're going to build up the difference quotient for that function. The trick is to start with the numerator of that difference quotient, g of x plus h minus g of x. That is this difference of integrals.
Where is H coming from?
Well, remember, so here, let me write this out. We can annotate a little better if we write it ourselves. So the proof of FTC1. Remember, by definition, g primed of x would be the limit as h goes to 0 of g of x plus h minus g of x all divided by h. That's the limit definition of the derivative. So we're starting way back there. And the way we're going to kind of get to calculating this is by first working with the numerator. So since g of x is the integral from a to x of f of t dt, g of x plus h would be the integral from a to x plus h of f of t dt. So g of x plus h minus g of x is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. So the h is just coming from the limit definition of the derivative. This is what we're going to build up. And then because g of x is the integral from a to x, the variable here is the upper bound. G of x plus h would be the integral from a to x plus h. And then to start working with this, I can split this up using that property of definite integrals. Remember, the integral from a to b can be written as the integral from a to c plus the integral from c to b. And I'm going to split it up at x. So you see here, this is what they're doing. They take the integral x plus h, and they apply it. They're going to subtract this guy off, which is the same thing as saying you're going to split this up. So let me, what do they do? Well, they're doing it a little bit differently. So they're going to split up the integral from a to x. Is that what we end up doing? X to x plus h is what they want to get. Oh, no, this is what I see what they're doing. Yeah, okay, this is fine. So they split this guy up as the integral from a to x plus the integral from x to x plus h. So they rewrite this first guy as integral a to x f of t dt plus the integral from x to x plus h f of t dt. So this, they're like thinking of c as x. Integral a to c plus integral c to b is the integral a to b. And then this guy is still just chilling. Minus integral a to x f of t dt. This is kind of clever. What that means, this piece and this piece cancel, right? They're the same thing. It's just plus this thing minus that same thing. So we're just going to be left with the middle term. Integral x to x plus h of f of t dt.
How do we know that it's okay to just split it in the middle like that? Because just visually speaking, what would this even look like on a graph? Just because it seems like the rule generally says that you can graph literally any number c. It doesn't even have to be between a and b. So how does that work?
Well, we worked through that last time, so I don't want to spend too much time justifying the split in terms of like whether that thing is between a and b or not. But here's the integral from a to x plus h. And that is the same. X here really is between a and a plus h. So it's not hurting us to, we don't have to like worry about this being over here. X plus h is bigger than x. So the integral from a to x plus h is the integral from a to x plus the integral from x to x plus h. That's the nicest way to think about it.
Okay, yeah, that actually makes sense.
Yeah, it's not too bad.
Thanks.
So we split this guy into these two. And then the first of those two cancels with the thing we're subtracting. So we're just left with this. From there, we're going to estimate this integral using the inequalities that we talked about in section 5.2. So remember, back in section 5.2, we had this theorem that said if little m is the min and big M is the max for your integrand, then the integral can be bounded below by little m times the width and bounded above by big M times the width. Yeah, Daniel's got the crucial question there. What if h is negative? It's true that when we think about this limit, lim h to 0, we should be thinking about both the left and right limit. So h could be negative in theory, and that would put x to the right of x plus h. But remember, one of the things we spend a good deal of time on in section 5.2 is justifying that the integral split is kosher, even if c is outside the interval a to b. So if h is negative, then it's true that x would be over here to the right of a plus h. But that would still be okay, because you'd have the integral from a to x being the integral all the way out to here, and then the integral from x to x plus h being the backwards oriented integral here. And those would subtract, and you'd still be measuring the same area. So this split is kosher, even if h is negative, for precisely the reasons we talked about in 5.2. That you can do the integral from a to b as integral a to c plus integral c to b, even if c is outside the interval ab. Right. Let's take what we have so far. I have the numerator of my difference quotient. Let's say, therefore, g of x plus h minus g of x all divided by h. We know that's the same as 1 over h times g of x plus h minus g of x, just a little algebra. And then g of x plus h minus g of x is this thing. So this is 1 over h times the integral from x to x plus h of f of t dt. Now remember, f, we are assuming, is a continuous function on the closed bounded interval ab, which means it has a max and it has a min, right? An absolute max and an absolute min. So we're going to let little m be the min and big M be the max. So let's say it like this. Since little f is continuous, we're not going to let little m be the min on AB. It's, I'll say this, attains an absolute min, little m, and an absolute max, big M, on the interval x to x plus h. And yes, there is some subtle stuff that we would need to be careful about. Again, if h is negative, you'd have to split the argument into cases. So for our purposes here, go ahead and assume h is positive. This would mean, so by our estimation theorem, from section 5.2, little m times the length of this interval, which is x plus h minus x, is less than or equal to the integral from x to x plus h of f of t dt is less than or equal to big M times the length of that interval, which is x plus h minus x. So this left-hand side here, this is m times h. This right-hand side here is big M times h. All right, this thing inside here is just h. So if I multiply through this by 1 over h, what I get is, well, they do it in separate steps. Let me see, is that going to be useful in some way? No, but we are going to have to come back and cite that. Yeah. So we get little m is less than or equal to 1 over h times the integral from x to x plus h f of t dt is less than or equal to big M. So this is little m times h, and when I divide through by h, that just becomes little m. This is big M times h. When I divide through by h, it just becomes big M, and this thing, when I divide through by h, is 1 over h times that integral. So we're starting to build up the thing we want. This thing here is this thing here. It's going to let us get a bound on the possible values of that derivative. Remember what the word attains means. It means that this function actually hits that min and actually hits that max. And your book writes this by saying that min is f of u for some variable u, or some constant u, sorry. And big M is f of v. So I can replace the little m by f of u and the big M by f of v. So we'll say this little m is f of u and big M is f of v. So that min is actually a function value, that max is actually a function value. Little m is f of u. This thing in the middle is my difference quotient. So I'll go ahead and write it as that, g of x plus h minus g of x all over h. And big M is f of v. Remember what we're aiming for here. I want to show that g primed is f of x. And remember here that u and v are in the interval x to x plus h. So what I want you to do now is think about it like this. For every number h, I can find a u and a v so that this is true. And those numbers u and v are both stuck between x and x plus h, whichever one is bigger, doesn't matter. As this interval shrinks, so let me say, as I draw this picture, the picture isn't necessary, but it will help, I think. Now maybe U is here and V is here. All right, maybe my min is attained over here and my max min is attained here and the max is attained here. As h goes to 0, this interval is going to squeeze down, right? This guy is going to come over, which is going to squeeze this whole interval down into a point. So as h goes to 0, what happens to u and v as this bracket comes over?
They get closer together.
They get closer together, true. And they also both get closer to some particular number. So this is fixed.
Won't they also get closer to 0?
This moves to the left as h goes to 0. So you imagine this bracket coming into the left. It's going to squish u and v and make everything pile up onto x. This thing holds still here. It's like a concrete wall. This is like a hydraulic press coming in from the left. It's going to smash u and v into x. Thus, as h goes to 0, both u and v go to x. Yeah, Talia's got it in the chat there. Yes, the garbage press from Star Wars. I gotta say, total random aside, and I apologize in advance for this. Since you mentioned Star Wars, I've recently been playing a video game called Jedi Fallen Order. I don't know, Star Wars games really been bad for a long time. Like I never bothered with any of the EA games. Holy shit, Fallen Order is amazing. It's like Dark Souls, but Star Wars, it's incredible. If you're into that stuff, Star Wars or video games, strongly recommend, strongly recommend. Free on Game Pass right now. Incredible game. All right. So yes, like the garbage press from Star Wars, as Sarah said, this thing is going to come over and compact u and v into x. They can't get outside this interval because they're the x values where f attains its min and its max on that interval. So for every number h, there are a u and a v where f attains its min and its max on the interval x to x plus h. And as h goes to 0, that interval is shrinking down to the point x, which means u and v got to go with them. So if I take limits everywhere in this expression using the squeeze theorem, if I take limits everywhere here using the squeeze theorem, I get a couple things. The outer guys are both going to the same place. U and v both have to go to x, which means f of u is going to go to f of x, and f of v is going to go to f of x. The squeeze theorem guarantees that if the outer things are the same, then the limit of the inner thing must exist, which would mean that g is differentiable. And by definition, the limit of that thing in the middle is g primed. And there's only one way for an inequality like this to be true. G primed of x is both bigger than or equal to f of x and less than or equal to f of x. This means that g primed of x must be equal to f of x, and that's the proof. So this is the fundamental theorem of calculus. And while this one is not the one that we use most of the time, the fundamental theorem of calculus part 2 is the one that's like, has a lot of utility down the road. Part 2 is proved from part 1. So it's really, this is the one that gets the job done. So the result here is just that if you define a new function as the integral from some constant to x of your old function, that new function is an antiderivative for the old function. So integration is the opposite of differentiation in a sense. When you integrate a function, the thing you get is an antiderivative for the original function. And that's a big deal because so far integration for us has just meant finding an area. This connects the idea of an area to the idea of an antiderivative. And that's going to be your bread and butter in the first third of Calc 2. In fact, a little more than that. Okay. Now you can get really fiddly here with deltas and epsilons, but there's no need. The result here is just what we want, that the thing inside is g primed, and that has to be equal to f of x. So let me do 1 or 2 more examples of FTC part 1, and then I'll show you FTC part 2. So we did a simple example a second ago. Do another simple example. Let's calculate g primed of x, where g of x is the integral from, say, 1 up to x of the square root of t squared plus 1 dt. Again, the main thing here is that when you differentiate this, which means differentiating this, all you're really going to do is take this function and plug in this variable. So by FTC1 with little f of t equal to the square root of t squared plus 1, g primed of x has to be little f of x, which is the square root of x squared plus 1. So you just take this variable up here and plug it into this function. That is the derivative of this thing. These can be phrased in different ways. I could say calculate d dz of the integral from 0 to z of e to the negative t squared dt. Same thing. Here your little f is e to the negative t squared. This whole thing I would call g of z. And it's a one-line thing by FTC1 d dz integral 0 to z e to the negative t squared dt is just e to the negative z squared. You just take that variable that is your upper bound and plug it in. Done. I said that these can be extended through the chain rule. These can also be extended through the properties of the integral. Let me show you 1 or 2 things like that. Maybe just one. This time I'll rephrase it like this. Find g prime of x, where g of x is the integral from x to 2 of the inverse tangent of t dt. So this isn't quite ready for FTC1 yet.
Gx is equal to minus integral 2 to x.
Yep, that's it exactly. So first I rewrite this, the integral from x to 2 of the inverse tangent of t dt as negative integral 2 to x inverse tangent of t dt. So g prime of x would be d dx of negative integral 2 to x inverse tangent of t dt. Should be negative, oops, sorry, d dx integral 2 to x inverse tangent of t dt. And now the derivative on the far bottom right, that is ready for FTC. This is the derivative of the integral from some constant up to x of this guy. So this would be negative inverse tangent of x. And you can imagine we can ask questions about increasing and decreasing here, all of the regular derivative stuff. I could ask you for the tangent line to this function, right? And you would use the fundamental theorem of calculus to cook up its derivative and then plug in whatever. Get your slope. All the standard derivative stuff we can do in this context as well.
I have a question for the top. The calculate dd is that integral 0 to is that, yes, this one. It doesn't need to use the chain rule here, right? If the integral 0 to e to the x, that need to use the chain rule in the question, right?
So we don't actually need the chain rule here because the variable that I'm differentiating with respect to is not t, it's z. So it's like I'm differentiating this, not this. If I wanted to differentiate e to the negative t squared, that would require the chain rule. But really what I'm doing is differentiating the integral. That's kind of the take home. And that's why I like this other way of writing it. So remember the kind of alternate way of writing FTC1 is to say that d dx of the integral from a to x, f of t dt is just f of x. See, there's no f primed here. I'm not differentiating the function inside. Really, I'm just differentiating the integral.
Yes.
Yeah, it's cool, right? And so the lesson here is that the integral and the derivative undo one another. They're inverse operations. In the same way that like squaring and the square root are inverse operations, the derivative and the integral are inverse operations. And you can study algebras of these things, algebras of operators. And it's actually a very big field in math and physics. Okay, but let's see how this interacts with the chain rule, because it does. So FTC1 and the chain rule. So remember what the chain rule says. It says if you want to differentiate a composite function. Oh, let me come back here. So the negative came because this integral isn't ready for FTC1 yet. It's got a variable as the lower bound and a constant as the upper bound. And in order to use FTC1, I need it the other way around. I need a constant down here and a variable up here. So the first thing we did is we took this integral and we flipped it over. And by flipping over that integral, a negative pops out. So first I kind of simplify this to negative integral 2 to x. And then when I differentiate that negative, it's just a constant multiple. It will come along for the ride. Yeah, it's sneaky. There are other flavors of this. Like I could have the integral from x to x plus 7 or something, and then you would need to split it up and flip one of them over. But the idea is you can use all of those properties of integrals to dissect the original function and put it into the form that you need for FTC1. All right, let's see how this thing interacts with the chain rule. So remember what the chain rule says. I'm sure you all have plenty of practice using it. I know you have plenty of practice using it. But this says if you want to take the derivative, so I'll say it like this: if u equals u of x is a function of x, then the chain rule says that d dx of f of u is f primed of u times u primed. The way this works with the fundamental theorem of calculus if u is a function of x, say, and g of x is the integral from a to u of f of t dt, kind of like, remember the integral is like the outer function here, and the inner function is u. And that means that g primed of x would be the derivative of the outer with the inner left alone. That would be f of u times the derivative of the inner, which would be u primed. This one gives people a bit of a hard time. So I want to show you a couple little examples. So I can try to calculate g primed, where g is the integral from 0 to x cubed of sine t dt. So here, remember the integral is the outer function, right? So if I were to differentiate this with respect to u, I would just get little f of u. That's what's going on. So FTC1 says, well, if I were to differentiate this with respect to u, imagine I just took d du of this thing. By FTC1, that would just be f of u. Maybe let me annotate here. So kind of differentiating the outer and leaving the inner alone means just erase the integral and plug u in here.
I have a question. Is it for the integral, if dd something always that look like the u is always in the integral, the upper of the integral u. So yes, always dd and the upper of the integral.
Yes, that's true. So the derivative you're taking here, this variable, needs to be whatever the thing is up here. And I agree, the notation is confusing. I think once we have FTC2, I'll be able to show you this kind of in light of that, and it will be a little easier to understand. So let me get through this example, then I'll give you FTC2, and we'll have a new way to think about it. So here we'd say by FTC1 and the chain rule, g primed of x, if I differentiate the outer thing, which is the integral, leaving the inside alone, that would just be sine of x cubed. But then by the chain rule, I need to multiply by the derivative of x cubed. And that's the sine of x cubed times 3x squared. So essentially, it's the same thing, right? When you differentiate the integral, you're going to take whatever it is that's up here and plug it in here. But then if this thing is a function rather than just x, you need to multiply by its derivative. So I take the x cubed, I plug it in here, that's sine of x cubed. That's like the derivative of the outer with the inner left alone. And then I multiply by the derivative of the inner, and the inner is this thing.
Why this one you use the chain rule, but before you don't use chain rule? Is it because it's a x cube is a function? It's not.
Right.
It's not only x. If only x, just sine x. That's all. But
yeah, because this is a function of x, not just x. Exactly what you said, you think is correct, and that kind of answers to Leah's question too. We only need the chain rule here if the upper bound is a function rather than just the variable.
I have like a quick question.
Yeah.
So I get that you're saying like the derivative and the integral kind of like cancel each other out, but I was confused, I guess, about how you got the, like, how you can say, I guess, is g prime, like, was the end result, like, how is it, I guess, like, where does the g prime come from?
Well, remember, we're thinking of the whole thing as being g. So this whole thing is g.
Mm-hmm.
And this u up here is a function of x. So g is the integral from a all the way up to u of x of little f dt. So I just, if you prefer to use the operator notation and just say that ddx of this thing is f of u times u prime, that's fine. But oftentimes we like to label this whole thing as a new function, and we call that new function g.
Okay. So I guess just to make sure, so that whole proof that you went through kind of, I guess, explains like why you're able to say, or like you end up with like, I guess, the derivative of the function. Exactly.
Yeah.
Okay.
Yeah, exactly. Yep. So the kind of, it would be very hard to prove that theorem in the operator notation.
Yeah. Okay.
So in order to kind of, just like when we proved the product rule and quotient rule, we called that combination a new function. Here we're going to call this weird combination of stuff by a new name, and that way we can write stuff down about it a little easier. But that's all. It's just a label.
Okay.
All right. So let me go ahead and show you the second fundamental theorem, and then we'll see how these interact with each other. This one's even simpler. He just says if capital F is any antiderivative for little f then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. And this is the main tool you'll use to evaluate definite integrals moving forwards. So thus far, anytime we need to evaluate a thing like this, we either have to interpret it in terms of areas or write out a Riemann sum. But now we have a new way to do it. Now, when you want to evaluate a definite integral, the game is to find an antiderivative and then plug in the bounds and subtract. And there's a special notation for this. You'll often see that difference, f of b minus f of a, written as capital F of x with this bar from a to b. Or sometimes people write it in brackets, capital F of x with a and b like this. Because the way, kind of the order you usually do things here, if somebody hands you an integral like this, you first work really hard to find an antiderivative for this guy. And once you find that antiderivative, you just want to write him down. So without worrying about plugging in the bounds, you just write down the antiderivative and you say, okay, next I'm going to evaluate from a to b. Again, let me show you a quick example. And then we'll take a look at the proof. So if I want to evaluate the integral from 0 to pi of sine x dx, I can do that by finding an antiderivative for sine. So integral 0 to pi of sine x dx, my little f here is sine x. So an antiderivative, and you can use any antiderivative.
Negative cosine?
Minus
Oh,
cosine.
okay.
Yeah. F of x would be negative cosine of x. So I can say that this integral is negative cosine of x evaluated from 0 to pi. And that is just the notation, right? So you want to have your antiderivative step as its own thing. And then we evaluate. So that's negative cosine of pi minus negative cosine of 0. F of b minus f of a. The cosine of pi is -1, so this is negative -1 minus negative cosine of 0 is 1. So that's 1 plus 1, which is 2. So the exact area under the sine curve from 0 to pi is 2. And boy, let me tell you, you're going to be doing a lot of this stuff in Calc 2. Calc 2 is, again, pretty much all integrals for the first third of the class. And every time you do an integral in Calc 2, you're using FTC2.
Could you show me the homework 18, the question 18?
Let me take a super quick peek because I do want to show you the proof here. Tell you what, let me log in here and we'll come back to this at the end of class. That way, if we go over a bit, we can do it then. Remind me when we finish up that you want to do that, and we will. We do need to look at the proof of the second theorem, and it's not too bad. Yeah, we can do all sorts of stuff here. So we're going to begin by, we're going to use part one. That's the idea. And we're going to begin by introducing a function g, which we know is an antiderivative. So let me FTC2. Let g of x be the integral from a up to x of little f of t dt. By FTC1, g primed is equal to little f. So g is an antiderivative. For little f. And we know that antiderivatives, if you have two different antiderivatives for the same function, they differ by at most a constant. That's all they're saying here. Plus if big F is any other antiderivative, then big F, I should say, big F of x is equal to g of x plus some constant. My aim here is to show that the integral from a to b is big F of b minus big F of a. They're going to show that this constant isn't really relevant. So you plug in a. Oh, there's something kind of clever here. 6, 8 equals 0. Yeah, okay. Is this? Yeah, okay. Now, g of a, since g is defined to be the integral from a to x, is the integral from a to a of f of t dt. And we've seen previously that the integral from somewhere to that same place, right? There's no width there. That is necessarily 0. Therefore, f of b minus f of a, because any antiderivative f has to be g of x plus c for some constant c. This would be g of b plus c minus g of a plus c. And distributing the negatives, this is g of b plus c minus g of a minus c. The c's cancel. And we know that g of a is 0. That's what we showed here. So these cancel. G of a is 0. So you just get g of b. But by definition, g of b is the integral, g of x is integral a to x. So g of b is the integral from a to b of f of t dt. And that's what we wanted to show, right? We wanted to show that this thing is equal to this thing for any antiderivative f, big F. So like I said, it's a very quick proof, and it just comes from the Fundamental Theorem of Calculus part 1. Part 1 is doing all the heavy lifting here. The main thing that we're using is that this function is a particular antiderivative for little f, and that is Fundamental Theorem of Calculus. That's the proof. And we'll get lots of practice using the theorem, just evaluating integrals by finding antiderivatives and plugging in bounds. The last thing I wanted to do for you here is to help you see that chain rule kind of through the lens of FTC2. I'm going to revisit. Chain rule and FTC1 using FTC2. Let g of x be the integral from a up to u of x of little f of t dt. We saw earlier that if you want g primed, that would be f of u times u primed. I want to really convince you of this. And let big F of x, I'll just say big F, be an antiderivative for little f. By FTC2, what do I have then? G of x, which is the integral from a up to u of x of little f of t dt, just copying that down. Applying FTC2 to this integral, that would be big F of x evaluated between the bounds a and u of x. I guess I should say big F of t here. It really doesn't matter. Big F of t. When you plug in those bounds, you get big F of u of x minus big F of a. So G is big F of u minus big F of a. This means that G primed of x would be d dx of big F of u of x minus big F of a. Oh my goodness. Oh wow, that looks amazing. Thank you, baby. Thank you, thank you. So now if I differentiate this with the normal chain rule, this is big F of t. So now if I use my normal chain rule on this, what does the normal chain rule say? Well, you differentiate the outer function, leaving the inside alone. So that would be big F primed of u of x. And then you multiply by the derivative of the inside, u primed of x. And the derivative of f of a is just a constant. That would be 0. Big F primed is little f. So this is little f of u of x times u primed of x. And I think this is the best way to really understand how the chain rule and FTC1 work together, is by kind of thinking through FTC2. Right, so the derivative of this thing is what you get by plugging this function in for t here, little f of u of x, and then multiplying by the derivative of u. This is what we had before. All All right, just another way of arriving at the same thing. Yeah, this makes a lot more sense to me also. I'll tell you, I didn't discover this way of thinking about things until years after I learned it in calculus. I remember thinking like, what the hell? But then when I was tutoring calc as an undergrad, close to the end of my undergrad, I ended up just like writing this down one day, trying to think about what the fuck was going on. And I go, oh, it's not that big F of A is 0. It's that when I differentiate, this piece is going to become 0 because this is a constant. A is a constant, so F of A is a constant, and the derivative of a constant is 0. And then this piece, I just differentiate using the normal chain rule. Ah, good stuff, right? Okay, so let's look at one more example of these FTC chain rule things and see if it feels a little less magical to us now. Let's find d dx of the integral from 0 to e to the x of, what would be fun? How about the square root of 1 minus t squared dt? So here my e to the x, this is u of x. And 1 minus t squared, that's my little f of t. So this derivative should be equal to f of u. So that's the square root of 1 minus e to the x squared times the derivative of u. And that's going to be the square root of 1 minus e to the 2x times the derivative of e to the x is just e to the x. And that's it, right? Really nothing too bad. I think it really does make a lot more sense through the lens of FTC2 than it does purely through the lens of FTC1, but they're very intimately related. All right, that's the big reveal, guys. That's it. This is the hot moment. It's going to be a long time before you get something this sweet in a calculus class again. The next step up from this is something called Stokes' theorem. Stokes' theorem is the first real generalization of the fundamental theorem of calculus. You will see cool stuff when you talk about power series in Calc 2 and lots of neat geometry things. And then in Calc 3, when you see Stokes' theorem, that's the first tool that really takes this to another level. From here until you start talking about sequences and series, the game is going to be learning how to calculate antiderivatives, getting really, really good at finding integrals. It turns out it's hard. It's wicked hard. We've got those nice antiderivative rules that Talia shared with us last time. But beyond those, things get wonky. Later in this semester, I will teach you the first big trick for finding antiderivatives, something called U substitution. We'll get there when we get there. But it's going to be a little while. Before that, Daniel is going to teach us about indefinite integrals and the net change theorem. And Daniel, since we did make it nice and clean all the way through 5.3 today, that means the natural move would be to have you do that on Friday. Are you still comfortable with that? Maybe. Yeah, so section 5.4 is next, and that is on the net change theorem and indefinite integrals. We've met once to talk a little bit about this, but I'm not 100% sure how ready you are. So Daniel, I don't know if you can hear me okay right now, but please reach out to me. Come by office hours today if you can. Let's just make sure that you're ready. If you're not, we can try to shuffle things around a little bit. But we would like to do that on Friday for our next meeting, if you're still okay with that. Okay, do me a favor, just communicate the material that you have to me somehow. If you can come by office hours today so we can do like a test run, that would be great. If you can't do that, maybe send me, I get that, yeah, it's a rough rough time of the semester. So that's why I'm trying to just check up and make sure. Okay, go ahead and send that to me then as soon as you can. And we can talk about it a little bit tomorrow. If we need to arrange an extra meeting tomorrow, I am free from like 10 to 11 in the morning. I don't imagine if you're planning to do it tomorrow that it will be ready by then, but we can maybe meet in the afternoon. I gotcha. Okay. Yeah, just send it to me in an email and I'll look over it and send you some feedback, and hopefully we can find a little bit of time to talk through Zoom or something like that between now and Friday. It would have to be either tomorrow between 10 and 11 for me or sometime later in the afternoon. So send me an email with the content when you have it. And in that email, also let me know when you're free to meet, even if it's that same day, and we'll figure something out just to make sure everything goes smooth, okay? That sounds good. Alrighty, I'll watch for your message and I'll see the rest of you next time. Everybody take care.